At the end of the 19th century, physics appeared to be a finished science. Many leading physicists believed that the fundamental laws governing nature had already been discovered, and that future work would merely refine measurements to greater precision. Newton's laws of motion explained mechanics with extraordinary accuracy. Maxwell's equations unified electricity, magnetism, and light, and thermodynamics described heat and energy flow with remarkable success. To the scientific community of the time, the universe seemed orderly, predictable, and fully comprehensible through classical principles. Yet beneath this confidence, small experimental anomalies were quietly undermining the very foundations of physics. One of the most troubling issues involved the nature of radiation and matter. Experiments studying blackbody radiation revealed results that classical physics could not explain. According to established theory, a heated object should emit increasing amounts of energy at shorter wavelengths, eventually producing infinite energy, a prediction later called the ultraviolet catastrophe. This was not just a minor error, it was a catastrophic failure of theory. At the same time, atomic physics faced a similar dilemma. If atoms followed classical laws, electrons orbiting a nucleus should continuously radiate energy and spiral inward, causing atoms to collapse almost instantly. The stable matter observed everywhere in the universe directly contradicted this prediction. These failures signaled that classical physics, despite its elegance and past triumphs, was fundamentally incomplete. However, the implications of this realization were deeply unsettling. The classical world, you had been built on determinism, continuity, and certainty. Energy was assumed to change smoothly. Particles had well-defined positions and velocities, and the future behavior of a system could be predicted exactly if its present state was known. The growing contradictions suggested that nature might not obey these comforting assumptions at the smallest scales. It was into this period of intellectual tension that Niels Bohr was born in 1085 in Copenhagen, Denmark. His upbringing played a crucial role in shaping the way he would later approach scientific problems. Bohr's father, Christian Bohr, was a distinguished physiologist who encouraged open discussion and critical thinking. Scientific debates were common in the Bohr household, and young Niels was exposed early to the idea that knowledge advanced through questioning, not blind acceptance of authority. His mother, Ellen Adler Bohr, came from a family deeply engaged in education and culture, further enriching his intellectual environment. Bohr's early education reflected both his analytical talent and his philosophical curiosity. He excelled in mathematics and physics, but was equally drawn to deeper questions about meaning, interpretation, and the limits of knowledge. Unlike many scientists who focused narrowly on calculation and experimentation, Bohr possessed a rare ability to reflect on the conceptual foundations of science. This dual mindset would later become essential as physics entered territory where intuition failed and interpretation mattered as much as equations. As a university student at the University of Copenhagen, Bohr initially worked on problems related to classical physics. His doctoral research focused on the electron theory of metals, an area deeply rooted in classical ideas. However, even during this early stage, Bohr encountered inconsistencies between theory and experiment that could not be ignored. These experiences planted the seeds of doubt that would eventually lead him away from strict classical thinking. A pivotal moment in Bohr's development came when he traveled to England to study under J. Thomson at the Cavendish Laboratory, the birthplace of the electron's discovery. Thomson was one of the most influential experimental physicists of the era, yet Bohr found that experimental work alone did not satisfy him. He was more interested in understanding the underlying principles governing atomic behavior than in performing laboratory measurements. This intellectual mismatch initially made Bohr feel out of place, but it also clarified his true strengths. Bohr's next move proved decisive. He went to Manchester to work with Ernest Rutherford, whose nuclear model of the atom had recently revolutionized atomic theory. Rutherford's experiments had shown that atoms consist of a small, dense, positively charged nucleus surrounded by electrons. While this model explained scattering experiments, it introduced a severe theoretical problem. According to classical electromagnetism, electrons orbiting the nucleus should emit radiation continuously, lose energy, and crash into the nucleus. Rutherford himself acknowledged this flaw, but had no solution. Bohr immediately recognized that Rutherford's atomic model, though experimentally sound, was theoretically unstable under classical laws. This realization struck at the heart of the atomic problem. Bohr understood that merely adjusting classical equations would not solve the issue. A more radical approach was required, one that accepted the experimental facts while abandoning classical assumptions where necessary. At the same time, Max Planck's work on blackbody radiation had introduced a strange and controversial idea. Energy could be emitted or absorbed only in discrete quantities, later called quanta. Planck himself viewed this as a mathematical trick rather than a statement about physical reality. Many physicists hoped the idea would eventually be replaced by a classical explanation. Bohr, however, took the quantum concept seriously and began to consider its deeper implications for atomic structure. Bohr's genius lay in his willingness to combine seemingly incompatible ideas. He accepted Rutherford's nuclear atom, which was grounded in experimental evidence, and merged it with Planck's quantum hypothesis, which challenged classical continuity. This combination required extraordinary intellectual courage. It meant accepting that the classical description of motion failed at the atomic level and that nature behaved differently on small scales. Crucially, Bohr did not reject classical physics outright. Instead, he treated it as an approximation that worked only under certain conditions. This nuanced perspective allowed him to retain the successes of classical theory while explaining its failures. Bohr proposed that electrons could occupy only certain allowed orbits around the nucleus, and that these orbits were stable despite violating classical expectations. While in these allowed states, electrons did not radiate energy. Radiation occurred only when electrons transitioned between orbits, emitting or absorbing fixed amounts of energy. This idea represented a complete departure from classical causality and continuity. The electron's motion could no longer be described as a smooth trajectory governed by Newton's laws. Instead, atomic behavior involved sudden jumps and discrete changes that had no classical explanation. Bohr understood that this was not merely a technical modification, but a conceptual revolution. What is often overlooked is the philosophical struggle Bohr faced in arriving at this conclusion. He was deeply uncomfortable with abandoning classical visualization. Unlike later quantum physicists who readily accepted abstract mathematics, Bohr sought physical meaning and coherence. He wrestled with questions about what electrons were actually doing and whether such questions were even meaningful. This struggle shaped his later views on interpretation and measurement. Bohr's early work was met with skepticism and resistance. Many physicists found his ideas unnatural and unsatisfying. The notion that electrons could jump instantaneously between orbits without passing through intermediate states defied common sense. Yet Bohr remained confident because his theory explained observed spectral lines with remarkable precision. Empirical success became his strongest defense. This period marked Bohr's transition from a promising young physicist into a revolutionary thinker. He had entered science at a moment when old ideas were failing and new ones were desperately needed. Rather than clinging to established frameworks, Bohr embraced uncertainty and contradiction as clues to deeper truth. He recognized that the crisis in physics was not a temporary inconvenience, but a sign that humanity's understanding of nature needed to change at the most fundamental level. Equally important was Bohr's growing awareness that physics was not just about describing objects, but about describing what can be known about them. The breakdown of classical predictions forced physicists to confront the limits of observation and measurement. Bohr began to see that scientific theories were not mirrors of reality, but tools shaped by experimental conditions and human language. This realization would later become central to his philosophical contributions. By the time Bohr introduced his atomic theory, he was already thinking beyond atoms. He sensed that quantum ideas would have far-reaching consequences, not only for physics, but for how knowledge itself was understood. The collapse of classical certainty revealed a universe that was subtle, probabilistic, and resistant to simple description. Thus, Bohr's entry into science coincided with one of the greatest intellectual turning points in history. He did not create the crisis in classical physics, but he recognized its significance more clearly than most. Where others saw technical problems, Bohr saw a fundamental shift in the relationship between theory and reality. His early experiences, intellectual environment, and philosophical depth uniquely prepared him to navigate this transformation. By stepping into a world where classical explanations failed and daring to accept the quantum as real, Bohr laid the groundwork for an entirely new physics. This was not the end of his journey, but the beginning of a lifelong effort to understand and articulate the strange logic of the quantum world. The crisis that challenged classical physics became the stage on which Niels Bohr emerged as one of the most influential thinkers in the history of science. As Bohr's atomic theory began to circulate within the scientific community, its implications reached far beyond the immediate problem of atomic stability. What Bohr had effectively demonstrated was that classical physics could no longer claim universal authority. The laws that governed planets, projectiles, and mechanical systems failed completely when applied to the internal structure of atoms. This realization marked a decisive break in the history of science, one that forced physicists to confront the uncomfortable possibility that nature operated according to different rules at different scales. The resistance Bohr faced was not merely technical, but deeply psychological. Classical physics had offered a vision of the universe that was orderly, continuous, and fully intelligible through human intuition. Bohr's ideas disrupted this vision by introducing discontinuity and unpredictability at the most fundamental level of matter. Many physicists struggled to accept that electrons could exist only in certain allowed states, without any classical mechanism enforcing those restrictions. The idea that nature imposed limits without explanation seemed unsatisfactory and even unscientific to those trained in deterministic thinking. Yet Bohr remained unwavering, not out of stubbornness, but because experimental evidence consistently favored his approach. Atomic spectra, which had long puzzled scientists, were explained with remarkable accuracy using his model. Each spectral line corresponded precisely to a transition between energy levels, lending strong empirical support to the concept of quantization. For Bohr, this success confirmed that physics had to adapt to nature, not the other way around. What distinguished Bohr from many of his contemporaries was his refusal to oversimplify the conceptual consequences of his work. He did not treat quantum ideas as temporary fixes or mathematical tricks. Instead, he recognized that they signaled a profound transformation in how physical reality must be understood. This awareness placed Bohr in a unique position as both a physicist and a philosopher of science, even though he never considered himself a philosopher in the traditional sense. Bohr's thinking evolved as he grappled with the deeper meaning of quantum behavior. He became increasingly convinced that classical concepts such as position, trajectory, and causality could not be applied uncritically to atomic systems. These concepts were rooted in everyday experience and macroscopic observation, yet atomic phenomena lay far outside the domain where such experience was reliable. Bohr argued that demanding classical explanations for quantum events was not only futile but fundamentally misguided. This insight marked a turning point in Bohr's intellectual development. He began to shift his focus from constructing mechanical models of atoms to understanding the limitations of language and description in physics. If electrons could not be visualized as tiny planets orbiting a nucleus, then new ways of thinking were required. Bohr emphasized that scientific descriptions were constrained by the tools and concepts available to observers. At the atomic level, observation itself altered the system being observed, making classical objectivity impossible. During this period, Bohr's ideas increasingly influenced a new generation of physicists who were equally dissatisfied with classical explanations. Young scientists such as Werner Heisenberg and Wolfgang Pauli found inspiration in Bohr's willingness to question foundational assumptions. Bohr encouraged open discussion and welcomed criticism, believing that scientific progress depended on confronting contradictions rather than avoiding them. His approach fostered an environment in which radical ideas could flourish. The intellectual atmosphere surrounding Bohr's work reflected the broader transformation taking place in physics. As quantum theory developed, it became clear that Bohr's atomic model, while groundbreaking, was only a stepping stone. New mathematical formulations soon emerged that replaced visual orbits with abstract wave functions and probability amplitudes. Despite these developments, Bohr's early insights remained central, particularly his insistence that classical concepts had limited applicability. Bohr's response to these new theories demonstrated his adaptability and depth of understanding. Rather than defending his original model as final, he embraced its limitations and supported more advanced formulations. He recognized that scientific theories were provisional and subject to revision as knowledge advanced. This humility strengthened his influence, as it positioned him as a guide rather than a dogmatist. As quantum mechanics matured, the crisis that had initially exposed the weaknesses of classical physics evolved into a broader philosophical challenge. Determinism, once considered a cornerstone of science, gave way to probability and uncertainty. Bohr accepted this shift not as a failure of science, but as a more accurate reflection of nature's behavior. He argued that the role of physics was not to uncover hidden mechanisms behind phenomena, but to describe the conditions under which phenomena could be observed and measured. This perspective reshaped the goals of scientific inquiry. Instead of seeking a complete and objective picture of reality independent of observers, Bohr emphasized the relationship between experimental arrangements and observed outcomes. Knowledge became contextual rather than absolute. This idea was revolutionary, as it challenged centuries of scientific realism and forced physicists to reconsider what it meant to explain something scientifically. Bohr's growing influence extended beyond theoretical discussions into the institutional structure of physics. He established a research institute in Copenhagen that quickly became a center for quantum research. Scientists from across Europe traveled there to exchange ideas, debate interpretations, and collaborate on groundbreaking work. The institute embodied Bohr's belief that science progressed through dialogue and shared exploration rather than isolated genius. The Copenhagen environment reflected Bohr's personality and values. He encouraged informal discussion, tolerated ambiguity, and valued questions as much as answers. This atmosphere proved crucial in shaping the development of quantum mechanics, as it allowed unresolved problems to remain open rather than forcing premature conclusions. Bohr understood that uncertainty was not an obstacle to progress, but a driving force behind it. Looking back, it becomes clear that Bohr's entry into science coincided with a unique historical moment. The collapse of classical physics created a vacuum that demanded new ideas, and Bohr possessed the rare combination of technical skill, philosophical insight, and intellectual courage required to fill it. He did not merely respond to the crisis. He transformed it into an opportunity for deeper understanding. The early struggles Bohr faced shaped his lifelong approach to science. He learned that nature often defied expectations and that progress required abandoning deeply held assumptions. This lesson guided his later work and influenced his interactions with other physicists, particularly during debates over the interpretation of quantum mechanics. Bohr's commitment to intellectual honesty and openness became defining features of his career. By the time quantum theory became firmly established, the classical world had been irreversibly altered. The universe was no longer seen as a perfectly predictable machine, but as a complex system governed by probabilities and constraints imposed by observation. This transformation owed much to Bohr's early willingness to confront the inadequacies of classical physics and to take quantum ideas seriously. The significance of Bohr's early contributions lies not only in their technical achievements, but in their philosophical implications. He demonstrated that scientific revolutions are not merely changes in equations, but shifts in how reality itself is conceptualized. The crisis of classical physics revealed the limits of human intuition, and Bohr showed that accepting those limits was essential for progress. In this sense, Bohr's journey into science was inseparable from the broader evolution of modern thought. His work reflected a growing recognition that knowledge is shaped by perspective, context, and interaction. Physics, once seen as the most objective of sciences, became a field where interpretation mattered as much as measurement. Bohr did not resist this transformation. He embraced it. By navigating the collapse of classical certainty and helping to establish a new quantum framework, Bohr set the stage for everything that followed in 20th century physics. His early career illustrates how moments of crisis can give rise to profound innovation when met with openness and intellectual courage. The problems that once threatened to undermine physics instead became the foundation of a deeper and more nuanced understanding of nature. Thus, Bohr's entry into the scientific world was not simply the beginning of a career, but the emergence of a new way of thinking about reality. The crisis of classical physics was the crucible in which his ideas were formed, and through his response to that crisis, Niels Bohr helped redefine the very meaning of scientific explanation. When Niels Bohr introduced his atomic model in 1913, he did far more than propose a new picture of atomic structure. He challenged the deepest assumptions of classical physics and forced the scientific community to confront the possibility that nature behaved according to principles radically different from those governing the visible world. At a time when atoms were still largely mysterious, Bohr's model provided the first coherent explanation of how matter could be stable while emitting and absorbing energy in discrete patterns. Before Bohr's work, the atom was understood primarily through Ernest Rutherford's nuclear model. Rutherford had shown that atoms consist of a tiny, dense, positively charged nucleus surrounded by electrons. While this discovery was revolutionary, it immediately created a theoretical crisis. According to classical electrodynamics, any charged particle undergoing acceleration should emit electromagnetic radiation. Electrons orbiting a nucleus would therefore lose energy continuously and spiral inward, causing atoms to collapse in a fraction of a second. The very existence of stable matter contradicted this prediction. Bohr recognized that Rutherford's atom, though experimentally supported, was fundamentally incompatible with classical laws. Instead of attempting to fix this inconsistency within the classical framework, Bohr took a bold and unprecedented step. He proposed that classical physics simply did not apply to atomic motion in the same way it applied to macroscopic objects. This decision marked a turning point in the history of science, as it required abandoning long-held beliefs about continuity, causality, and determinism. The central idea of Bohr's atomic model was that electrons could exist only in certain allowed orbits around the nucleus. These orbits were not determined by classical mechanics, but by specific conditions that restricted the electron's energy to discrete values. While occupying one of these allowed orbits, an electron did not emit radiation, regardless of its acceleration. This postulate directly violated classical electrodynamics, but was necessary to explain atomic stability. Bohr further proposed that radiation occurred only when an electron transitioned between these allowed orbits. When an electron jumped from a higher energy orbit to a lower energy one, it emitted a photon with energy equal to the difference between the two energy levels. Conversely, when an electron absorbed energy, it could jump to a higher energy orbit. This explanation provided an elegant and precise account of atomic emission and absorption spectra, which had long puzzled physicists. What made this model particularly striking was its quantitative success. By applying his theory to the hydrogen atom, Bohr derived formulas that accurately predicted the wavelengths of spectral lines observed experimentally. These predictions matched known data with extraordinary precision, offering compelling evidence that his radical assumptions reflected physical reality rather than mathematical convenience. Yet Bohr himself was keenly aware that his model was conceptually unsettling. The idea that electrons could leap instantaneously between orbits without passing through intermediate states defied classical intuition. There was no physical mechanism explaining how or why these jumps occurred. Bohr accepted this lack of explanation as a temporary limitation, believing that deeper understanding would eventually emerge. What mattered most was that the model worked where classical theories failed. Bohr's willingness to prioritize empirical success over intuitive explanation distinguished him from many of his contemporaries. He understood that insisting on classical visualization could hinder progress when dealing with fundamentally new phenomena. This pragmatic approach allowed him to push physics forward even when the underlying concepts were difficult to interpret. Another crucial aspect of Bohr's model was its incorporation of Planck's quantum hypothesis. By relating the energy of emitted or absorbed radiation to the frequency of light, Bohr connected atomic structure directly to quantization. This connection unified previously separate areas of physics, linking atomic theory with radiation theory in a way that classical physics had never achieved. Despite its success, Bohr's atomic model was not universally accepted. Many physicists viewed it as an ad hoc construction lacking a solid theoretical foundation. Critics argued that Bohr had introduced arbitrary rules without explaining their origin. Bohr did not deny these criticisms. Instead, he acknowledged the provisional nature of his model. He viewed it as a necessary step toward a more complete theory, not a final answer. The controversy surrounding Bohr's model reflected a broader tension within physics. Scientists were struggling to reconcile experimental evidence with deeply ingrained conceptual frameworks. Bohr's work forced them to confront uncomfortable questions about the limits of classical reasoning. Was it reasonable to demand classical explanations for phenomena that lay outside the domain of classical experience? Bohr believed it was not. Bohr's approach to atomic theory also revealed his emerging philosophical perspective. He began to see that scientific models were not literal pictures of reality, but tools for organizing and predicting observations. The success of the atomic model did not depend on whether electrons truly moved in neat circular orbits, but on whether the model accurately described measurable outcomes. This shift in thinking paved the way for later developments in quantum mechanics. As the implications of Bohr's model became clearer, it inspired a wave of further research. Physicists began exploring how quantization might apply to more complex atoms and other physical systems. Although Bohr's original model could not fully explain multi-electron atoms, it established principles that guided subsequent theories. The idea that energy levels were quantized became a cornerstone of modern physics. Bohr's model also had profound educational and cultural impact. For the first time, students and scientists had a concrete framework for understanding atomic behavior. Even though the model was eventually replaced by more sophisticated theories, it remained an essential stepping stone in the development of quantum mechanics. Its simplicity made abstract quantum ideas accessible and demonstrated the power of abandoning classical assumptions when necessary. Throughout this period, Bohr maintained a cautious and reflective attitude toward his own work. He resisted the temptation to overstate its significance or claim finality. Instead, he emphasized that physics was undergoing a transition and that new concepts were still taking shape. This humility earned him respect and trust within the scientific community, even among those who remained skeptical. Bohr's atomic model also highlighted the growing importance of theoretical creativity in physics. Unlike classical theories, which often emerged gradually from accumulated observations, quantum ideas required imaginative leaps that challenged conventional thinking. Bohr's success demonstrated that such leaps, when guided by empirical evidence, could lead to profound insights. As experimental techniques improved, new data continued to support the existence of discrete energy levels within atoms. These findings reinforced the core principles of Bohr's model, even as its specific details were refined or replaced. The model's enduring influence lay not in its literal accuracy, but in its demonstration that quantization was a fundamental feature of nature. By proposing a stable atomic structure based on quantum principles, Bohr resolved one of the most pressing problems in early 20th century physics. He showed that atomic stability and spectral regularities were not mysteries to be explained away, but natural consequences of quantized energy. This achievement transformed atomic physics from a collection of puzzles into a coherent field of study. In retrospect, the revolutionary nature of Bohr's atomic model becomes even more apparent. It marked the moment when physics definitively broke with classical continuity and embraced discreteness as a fundamental principle. This shift laid the groundwork for all subsequent developments in quantum theory. Bohr's contribution was not merely technical, but conceptual. He demonstrated that progress sometimes requires accepting ideas that seem illogical or incomplete by existing standards. His atomic model embodied this lesson, serving as both a solution to specific problems and a symbol of a broader scientific revolution. As Bohr continued his work, he remained deeply engaged with the implications of his model. He understood that its success raised new questions about the nature of reality, measurement, and explanation. These questions would later become central to quantum mechanics and the philosophical debates that surrounded it. Thus, the atomic model introduced by Niels Bohr stands as one of the most transformative ideas in the history of science. It resolved long-standing contradictions, introduced quantization into atomic structure, and forced physicists to rethink their assumptions about motion and energy. This was only the beginning of Bohr's impact, but it was the moment when his revolutionary approach to physics first became unmistakably clear. As the scientific community absorbed the implications of Bohr's atomic model, its deeper significance began to emerge. What initially appeared as a clever solution to the problem of atomic stability soon revealed itself as a profound challenge to the very structure of physical explanation. Bohr had not merely adjusted existing theory, he had introduced a new logic for understanding nature at its most fundamental level. One of the most striking consequences of the atomic model was its rejection of classical continuity. In classical physics, motion was smooth and uninterrupted, governed by differential equations that described how systems evolved over time. Bohr's model replaced this smooth evolution with sudden, discontinuous changes. Electrons did not gradually lose or gain energy, they jumped abruptly between allowed states. These jumps had no classical cause and no temporal description, they simply occurred. This discontinuity unsettled many physicists because it undermined the principle of causality that had long been central to scientific reasoning. In Bohr's framework, the exact moment or mechanism of an electron's transition could not be predicted, only the probability of such a transition. This shift from certainty to probability marked a radical departure from the deterministic world that had dominated physics since Newton. Bohr understood that his model introduced unresolved tensions, but he did not attempt to conceal them. Instead, he openly acknowledged that the atomic model rested on postulates that could not be derived from classical theory. He argued that these postulates were justified by their empirical success and by the failure of all classical alternatives. This pragmatic stance reflected his belief that the role of theory was not to satisfy human intuition, but to account for observed phenomena as accurately as possible. The success of the model also revealed the limitations of visual representation in physics. Bohr himself warned against interpreting electron orbits too literally. While the image of electrons circling a nucleus provided a useful heuristic, it could not capture the true nature of atomic behavior. This caution anticipated later developments in quantum mechanics, where wave functions and abstract mathematical structures replaced physical pictures entirely. As researchers applied Bohr's ideas to other elements beyond hydrogen, the strengths and weaknesses of the model became increasingly clear. While it could be extended with partial success to ionized atoms, it struggled to account for the complexity of multi-electron systems. These difficulties did not diminish the model's importance. Instead, they highlighted the need for a more comprehensive theory that retained quantization while abandoning classical orbits altogether. Bohr welcomed these challenges as signs of progress rather than failures. He recognized that scientific revolutions unfold in stages, and that early models often serve as bridges between old and new paradigms. His atomic model fulfilled precisely this role, providing a conceptual link between classical physics and the emerging quantum framework. The influence of Bohr's ideas extended well beyond atomic theory. By demonstrating that physical laws could differ fundamentally across scales, Bohr opened the door to a new understanding of natural limits. The assumption that a single set of principles governed all phenomena gave way to a layered view of reality, in which different descriptions applied under different conditions. This perspective would later become central to modern physics. Bohr's model also played a crucial role in reshaping scientific methodology. It challenged the belief that theories must offer complete mechanical explanations for all processes. Instead, Bohr showed that it was sometimes necessary to accept formal rules that described outcomes without detailing underlying mechanisms. This shift had profound implications for how scientists evaluated theories, placing greater emphasis on predictive power and consistency with experiment. The atomic model also reinforced the growing recognition that measurement was not a passive act. The emission and absorption of radiation, central to Bohr's theory, depended on interactions between atoms and measuring devices. This dependence foreshadowed later insights into the role of observation in quantum phenomena. Bohr began to see that experimental arrangements were inseparable from the phenomena they revealed. As quantum mechanics developed in the following decade, Bohr's early work provided a conceptual foundation for new mathematical formulations. The introduction of wave mechanics and matrix mechanics replaced Bohr's orbits with probability amplitudes and operators. Yet these advanced theories preserved the core idea that atomic systems possess discrete energy levels and that transitions between them are inherently probabilistic. Bohr's response to these developments further illustrated his intellectual leadership. Rather than defending his original model as an endpoint, he actively supported the newer theories and worked to interpret their meaning. He understood that his atomic model had served its purpose and that progress required moving beyond it. This willingness to let go of earlier ideas demonstrated a rare commitment to scientific integrity. The model's influence on education and public understanding of science cannot be overstated. For decades, it provided a clear and compelling introduction to atomic structure, shaping how generations of students first encountered quantum ideas. Even after its limitations were recognized, it remained a powerful teaching tool that conveyed the essence of quantization in an accessible form. More importantly, the atomic model transformed the way physicists thought about explanation itself. It showed that nature could not always be understood through analogies drawn from everyday experience. Concepts such as orbit, trajectory, and force lost their universal applicability. In their place emerged a new emphasis on abstract relationships and measurable outcomes. Bohr's atomic theory also had far-reaching technological implications. By explaining the discrete energy levels of atoms, it laid the groundwork for understanding lasers, semiconductors, and atomic clocks. These technologies, which define modern life, trace their conceptual origins to the principles introduced in Bohr's model. What began as an attempt to solve a theoretical problem ultimately reshaped the technological landscape. As debates over the interpretation of quantum mechanics intensified, Bohr's early experiences with the atomic model informed his later philosophical positions. He had learned firsthand that demanding classical explanations for quantum phenomena led to contradictions. This lesson reinforced his belief that new conceptual frameworks were necessary and that clinging to outdated intuitions hindered progress. The atomic model thus occupies a unique place in the history of science. It was neither purely classical nor fully quantum, but a hybrid that bridged two eras. Its success demonstrated that bold theoretical innovation, grounded in empirical evidence, could overcome even the most deeply entrenched assumptions. By introducing quantized energy levels and rejecting classical continuity, Bohr fundamentally altered the trajectory of physics. He showed that atomic stability was not a mystery to be resolved within classical laws, but a clue pointing toward a new description of nature. This insight transformed atomic physics into a rigorous and predictive science. The broader significance of Bohr's work lies in its demonstration that scientific understanding evolves through conceptual disruption as much as through experimental discovery. The atomic model forced physicists to rethink what it meant to explain phenomena, to accept uncertainty, and to recognize the limits of classical reasoning. In this way, Bohr's atomic theory did more than solve specific problems. It reshaped the intellectual foundations of physics. It marked the moment when the quantum revolution became unavoidable, setting the stage for the full development of quantum mechanics. Through this revolutionary model, Niels Bohr established himself as a central figure in modern science. His willingness to challenge tradition, embrace uncertainty, and prioritize empirical truth over intuitive comfort exemplified the spirit of scientific progress. The atomic model remains a testament to the power of rethinking fundamental assumptions in the pursuit of deeper understanding. One of the most profound contributions Niels Bohr made to physics was the clear demonstration that energy at the atomic level is not continuous, but quantized. This idea, simple in statement yet revolutionary in consequence, provided the long-sought explanation for why atoms are stable and why matter does not collapse into chaos. Before the introduction of quantization, classical physics offered no satisfactory answer to these questions, and the existence of stable atoms remained a deep and unresolved mystery. In classical theory, energy was assumed to vary smoothly. An object could possess any amount of energy, and changes in energy occurred continuously over time. This assumption worked extremely well for macroscopic systems, such as moving objects, vibrating strings, or orbiting planets. However, when applied to atoms, it led to disastrous conclusions. According to classical electrodynamics, an electron moving around a nucleus is an accelerating charged particle, and accelerating charges must emit radiation. As the electron radiated energy, it would lose speed, spiral inward, and eventually crash into the nucleus. This process should occur extremely rapidly, meaning atoms should be inherently unstable. Yet matter clearly persists. The failure of classical physics to explain atomic stability indicated that a fundamental assumption had to be wrong. Bohr identified this assumption as the continuity of energy. Drawing inspiration from Max Planck's earlier work on blackbody radiation, Bohr proposed that energy exchange at the atomic level occurs only in discrete units. Electrons could not possess arbitrary energies. Instead, only specific energy values were allowed. This restriction was not imposed by mechanical forces in the classical sense, but by quantum conditions inherent to atomic structure. By introducing quantization, Bohr fundamentally changed how energy was understood. In his framework, electrons occupy distinct energy states that are sharply defined. While in one of these states, an electron does not radiate energy regardless of its motion. This single postulate resolved the problem of atomic collapse. Since electrons could not continuously lose energy, they could remain indefinitely in stable configurations. Atomic stability was no longer a mystery, but a natural consequence of quantized energy. The concept of discrete energy levels also explained another long-standing puzzle: the emission and absorption spectra of atoms. Experiments had shown that atoms emit light only at specific frequencies, producing sharp spectral lines rather than a continuous spectrum. Classical physics could not account for this behavior, as accelerating charges should emit radiation across a broad range of frequencies. Bohr's theory provided a direct explanation. When an electron transitioned from a higher energy level to a lower one, it emitted a photon whose energy exactly matched the difference between the two levels. Because only certain energy levels existed, only certain photon energies could be emitted. This relationship established a direct connection between atomic structure and radiation. Light was no longer viewed merely as a wave emitted by oscillating charges, but as a carrier of discrete energy packets linked to atomic transitions. This insight unified atomic physics and radiation theory in a way that had never been achieved before. Quantization also introduced a new type of stability that had no classical analog. In classical systems, stability arises from balance of forces and energy minimization through continuous motion. In atomic systems, stability arose from prohibition. Certain energy states were simply forbidden, regardless of how plausible they seemed from a classical perspective. The electron could not slowly drift toward the nucleus because there were no allowed energy states between the permitted levels. Nature imposed boundaries that could not be crossed. This idea challenged deeply held intuitions about motion and change. In everyday experience, objects move smoothly from one state to another. Bohr's atomic world replaced smooth transitions with abrupt jumps. These jumps had no duration and no intermediate stages. While unsettling, this picture was strongly supported by experimental evidence. Spectral lines appeared suddenly and discretely, not gradually, reinforcing the idea that energy changes at the atomic level were fundamentally discontinuous. Bohr understood that quantization was not a minor correction to classical theory, but a radical departure from it. He emphasized that classical concepts could still be used to describe experimental arrangements and measurement devices, but they could not fully describe atomic processes themselves. Energy quantization marked the boundary where classical language began to fail. Another crucial consequence of quantization was the emergence of natural scales in physics. Classical theories allowed quantities to vary freely, but quantum theory introduced fundamental constants that set limits on physical behavior. Planck's constant became central in determining the size of energy quanta and the spacing of atomic levels. This constant defined how strongly quantum effects manifested and explained why classical physics worked well at large scales while failing at small ones. Through quantization, Bohr showed that atomic stability was not accidental, but deeply rooted in the structure of physical law. Matter is stable not because electrons happen to remain in place, but because the laws of nature restrict what electrons are allowed to do. This insight transformed stability from a problem into a principle. The philosophical implications of this shift were immense. Quantization suggested that nature does not always permit smooth explanation. Instead, it enforces rules that may appear arbitrary but are consistently obeyed. Bohr recognized that these rules could not be justified through classical reasoning alone. They represented a new layer of description that required acceptance rather than mechanical explanation. Quantization also altered the relationship between prediction and certainty. While the allowed energy levels could be calculated precisely, the timing of transitions between them could not. Physics moved from predicting exact trajectories to predicting probabilities of events. This probabilistic element, introduced indirectly through energy quantization, would later become a defining feature of quantum mechanics. Importantly, Bohr did not interpret quantization as evidence of ignorance or hidden variables. He viewed it as a fundamental feature of nature. The inability to describe transitions in classical terms was not a temporary limitation, but a reflection of how the atomic world truly operates. This stance distinguished Bohr from many critics who hoped that a deeper classical explanation would eventually restore continuity. As quantum theory developed, energy quantization proved to be a universal principle. It appeared not only in atoms but in molecules, solids, radiation, and fields. The idea that systems possess discrete energy states became foundational to modern physics. Bohr's early work provided the first clear demonstration of this principle in action. The success of quantization in explaining atomic stability reinforced Bohr's broader belief that physics must adapt its concepts to nature rather than forcing nature into familiar frameworks. By accepting discreteness where continuity failed, Bohr opened the door to a more accurate and powerful description of reality. In the end, quantization transformed the atom from an unstable classical system into a coherent and predictable quantum entity. It explained why matter exists, why atoms emit light in precise patterns, and why classical physics breaks down at small scales. Through this single idea, Bohr helped reveal a universe governed not by smooth inevitability, but by structured possibility. This understanding of energy as quantized remains one of the cornerstones of modern science. It reshaped physics at its foundation and continues to influence how humanity understands matter, light, and the limits of knowledge itself. As quantum theory matured, it became increasingly clear that the revolutionary discoveries of the early 20th century demanded more than new equations. They required a fundamental reconsideration of how physical reality itself could be described. Niels Bohr emerged as the central figure in this transformation, not by adding new mathematical tools, but by redefining the relationship between observation, description, and reality. His principle of complementarity represented one of the most profound conceptual shifts in the history of science, altering how physicists understood the nature of knowledge at the quantum level. At the heart of complementarity was the recognition that quantum objects do not possess all classical properties simultaneously in a well-defined way. Experiments had shown that light and matter could exhibit both wave-like and particle-like behavior depending on the experimental setup. In classical physics, this duality appeared contradictory. Waves and particles were mutually exclusive categories, each defined by distinct properties. Bohr argued that this contradiction arose not from nature itself, but from the limitations of classical concepts when applied beyond their domain of validity. Bohr proposed that wave and particle descriptions are complementary, meaning that both are necessary to fully account for quantum phenomena, yet they cannot be applied at the same time. Each description is valid only within a specific experimental context. When an experiment is designed to measure particle-like properties such as position or impact, wave-like properties such as interference become inaccessible. Conversely, when an experiment reveals wave-like behavior, precise particle trajectories cannot be defined. These descriptions do not compete, they complete each other. This idea represented a radical departure from classical realism. In classical physics, objects were assumed to possess definite properties independent of observation. Measurement merely revealed what was already there. Bohr rejected this assumption at the quantum level. He argued that the properties of quantum systems are not independent of the experimental conditions under which they are observed. The act of measurement plays an essential role in defining what can be said about a system. Complementarity thus reframed the role of the observer in physics. Observation was no longer a passive process, but an active element in the phenomenon itself. This did not mean that consciousness influenced reality, but that measurement devices, which must be described using classical concepts, interact with quantum systems in ways that fundamentally limit what can be known simultaneously. The observer, the measuring apparatus, and the system under study formed an inseparable whole. Bohr was careful to emphasize that complementarity did not imply subjectivity or randomness in scientific knowledge. Instead, it imposed strict constraints on how knowledge could be obtained and expressed. Physical statements remained objective in the sense that they referred to reproducible experimental outcomes, but they were contextual rather than absolute. The meaning of a physical quantity depended on the experimental arrangement used to measure it. This perspective resolved many apparent paradoxes in quantum theory. Rather than attempting to force quantum behavior into classical categories, complementarity accepted that different experimental arrangements reveal different aspects of reality. The contradictions arose only when one tried to apply incompatible descriptions simultaneously. By respecting the limits imposed by quantum phenomena, physicists could achieve a consistent and coherent understanding of experimental results. Bohr's ideas were met with both admiration and resistance. Some physicists found complementarity vague or philosophically troubling, arguing that it abandoned the goal of describing an objective reality. Others saw it as an inevitable response to experimental evidence. Bohr defended his position by insisting that physics is concerned not with how nature is in itself, but with what can be said about nature. This distinction shifted the focus of science from metaphysical speculation to empirical description. The principle of complementarity also extended beyond wave-particle duality. It applied to other pairs of physical quantities, such as position and momentum, which cannot both be precisely known at the same time. This limitation was later formalized in Heisenberg's uncertainty principle, but Bohr provided its conceptual interpretation. According to Bohr, uncertainty was not due to experimental imperfection, but a fundamental feature of quantum systems arising from the complementary nature of physical descriptions. Bohr's interpretation emphasized that classical concepts remained indispensable, even though they were insufficient on their own. Measurement results must be expressed in classical language because experimental apparatus operates in the macroscopic world. However, classical concepts cannot be applied without restriction. Complementarity defined the conditions under which classical descriptions could be used meaningfully. This balance between necessity and limitation reflected Bohr's broader philosophical outlook. He believed that scientific progress often involves recognizing the boundaries of existing concepts rather than replacing them entirely. Complementarity did not discard classical physics, it contextualized it. Classical ideas remained valid within their domain, but their universal applicability was abandoned. The debates surrounding complementarity reached their peak in Bohr's famous exchanges with Albert Einstein. Einstein challenged the idea that quantum mechanics provided a complete description of reality, proposing thought experiments designed to reveal hidden variables or restore determinism. Bohr responded by carefully analyzing each scenario and demonstrating that Einstein's conclusions relied on incompatible experimental assumptions. These debates clarified and strengthened the concept of complementarity, revealing its power as an interpretive framework. Through these discussions, Bohr demonstrated that quantum mechanics did not undermine rationality, but required a new form of rational understanding. Instead of seeking a single, all-encompassing description, physicists had to accept multiple, context-dependent descriptions that together captured the full range of observable phenomena. This approach reflected a deeper humility about the limits of human knowledge. Complementarity also had implications beyond physics. It influenced philosophical discussions about language, logic, and epistemology. The idea that mutually exclusive descriptions could both be necessary challenged traditional notions of truth and objectivity. Bohr himself was cautious about extending his ideas too far beyond physics, but he recognized their broader significance. In practical terms, complementarity guided how physicists designed and interpreted experiments. It discouraged attempts to simultaneously measure incompatible quantities and provided a framework for understanding why such attempts failed. This guidance was essential as experimental techniques became increasingly precise and quantum effects more pronounced. Over time, complementarity became a cornerstone of the Copenhagen interpretation of quantum mechanics. While alternative interpretations emerged, Bohr's ideas continued to shape mainstream understanding. Even critics of complementarity were forced to engage with its insights, acknowledging the challenges it addressed. The enduring significance of complementarity lies in its redefinition of what it means to explain nature scientifically. It taught physicists that explanation does not always involve revealing hidden mechanisms, but sometimes requires accepting fundamental limits. By articulating these limits clearly and coherently, Bohr provided a stable foundation for quantum theory at a time when its implications threatened to fragment the field. Through complementarity, Niels Bohr transformed quantum mechanics from a collection of mathematical rules into a coherent world view. He showed that the strangeness of the quantum world was not a flaw to be eliminated, but a feature to be understood. This insight allowed physics to move forward without retreating into classical illusions or metaphysical speculation. In this way, complementarity stands as one of Bohr's greatest intellectual achievements. It bridged the gap between experimental evidence and conceptual understanding, offering a way to think clearly about a reality that resists simple description. By embracing the limits of knowledge, Bohr expanded the reach of science, revealing a universe richer and more subtle than classical physics had ever imagined. Few moments in the history of science rival the intellectual drama of the debates between Niels Bohr and Albert Einstein. These exchanges were not merely disagreements between two great physicists. They represented a clash between two fundamentally different visions of reality. At stake was nothing less than the nature of physical truth, the limits of human knowledge, and whether the universe was governed by certainty or probability. Albert Einstein, whose work had revolutionized space, time, and energy, was deeply uneasy with the emerging interpretation of quantum mechanics. Although he had contributed decisively to its foundations, Einstein never accepted the idea that chance played a fundamental role in nature. He believed that physical theories should describe an objective reality existing independently of observation. For Einstein, probabilities signaled incompleteness, not truth. Niels Bohr, by contrast, had come to accept uncertainty and probability as unavoidable features of the atomic world. His experiences with atomic structure and quantization had convinced him that classical expectations could not be imposed on quantum phenomena. Where Einstein sought hidden order beneath apparent randomness, Bohr argued that randomness reflected the limits imposed by nature itself. The tension between these views came to a head during a series of public discussions at scientific conferences, most famously at the Solvay conferences in the 1920s and 1930s. Einstein repeatedly presented thought experiments designed to show that quantum mechanics violated fundamental principles such as causality or conservation laws. His goal was to demonstrate that the theory must be incomplete and that a deeper, deterministic framework remained undiscovered. Bohr responded not with counterexamples, but with careful analysis of the assumptions underlying Einstein's arguments. Again and again, Bohr showed that Einstein's thought experiments relied on classical concepts applied in incompatible ways. By exposing these hidden contradictions, Bohr defended the internal consistency of quantum mechanics while reinforcing the need for a new conceptual framework. One of the central points of contention concerned the role of measurement. Einstein believed that physical properties existed prior to and independent of observation. From this perspective, measurement merely revealed pre-existing values. Bohr rejected this assumption, arguing that at the quantum level, physical properties are defined only within specific experimental contexts. Measurement does not uncover reality, it participates in its definition. Einstein famously summarized his discomfort with quantum mechanics by declaring that God does not play dice. This statement captured his belief that nature must ultimately be governed by strict laws, even if those laws were not yet known. Bohr's reply was equally memorable, urging Einstein not to tell God how to run the universe. Behind the humor lay a deep philosophical divide that neither side could bridge. One of Einstein's most significant challenges was the argument later known as the EPR paradox. Einstein and his collaborators proposed a scenario in which two particles interact and then separate, yet remain correlated in such a way that measuring one appears to instantaneously determine the state of the other. Einstein interpreted this as evidence that quantum mechanics was incomplete, since it seemed to allow information to travel faster than light or required the existence of hidden variables. Bohr's response to this challenge was subtle and conceptually demanding. He argued that Einstein's reasoning assumed the simultaneous reality of incompatible properties. According to Bohr, the correlations described in the paradox did not imply faster than light influence, but reflected the holistic nature of quantum systems. The experimental conditions defined what could be meaningfully said about each particle, and no contradiction arose when those conditions were properly accounted for. These debates were not resolved by rhetorical victory alone. Over time, experimental evidence increasingly supported Bohr's interpretation. Experiments confirmed quantum predictions with remarkable accuracy, while attempts to restore classical determinism consistently failed. Decades later, tests of quantum entanglement further demonstrated that the correlations Einstein found troubling were real features of nature, not artifacts of incomplete theory. Despite this, Bohr never claimed personal victory over Einstein. He held Einstein in the highest regard and viewed their disagreements as essential to the advancement of physics. Bohr believed that Einstein's relentless questioning forced quantum theory to clarify its foundations and strengthen its conceptual coherence. Without Einstein's challenges, quantum mechanics might have remained vague or poorly understood. The debates also revealed Bohr's unique intellectual style. He did not rely on mathematical dominance or authority, but on patience, clarity, and a deep sensitivity to conceptual nuance. Bohr was willing to spend hours refining arguments, examining assumptions, and clarifying language. His approach contrasted sharply with Einstein's intuitive and often visual reasoning, highlighting the diversity of scientific thinking. At a deeper level, the Bohr-Einstein debates reflected competing views of what science should aim to achieve. Einstein sought a complete description of reality as it exists independently of observers. Bohr argued that such a goal exceeded the limits of empirical science. For Bohr, physics was concerned with the conditions under which phenomena appear and can be communicated unambiguously. This shift redefined scientific explanation itself. The outcome of these debates shaped the dominant interpretation of quantum mechanics for generations. Bohr's perspective became central to how physicists understood measurement, uncertainty, and the role of classical concepts. Even those who remained dissatisfied with this interpretation were compelled to frame their alternatives in response to Bohr's arguments. Importantly, the debates did not diminish Einstein's stature or invalidate his concerns. On the contrary, they highlighted the depth of the conceptual challenges posed by quantum theory. Einstein's resistance underscored how radical the new physics truly was. That such a mind could not accept quantum mechanics without reservation demonstrated how profoundly it departed from classical thinking. Bohr's willingness to confront Einstein on equal footing cemented his role as the philosophical leader of quantum theory. He did not merely defend a set of equations. He articulated a new vision of knowledge that accommodated uncertainty without surrendering rigor. This achievement required not only scientific insight, but intellectual courage. The legacy of the Bohr-Einstein debates extends far beyond their historical moment. They continue to influence discussions about realism, determinism, and the interpretation of scientific theories. Modern debates about quantum foundations, information, and reality still echo the questions first raised in those early confrontations. In the end, the significance of these debates lies not in declaring a winner, but in recognizing how they shaped modern science. Bohr and Einstein represented two complementary attitudes toward knowledge, one seeking certainty beneath appearances, the other accepting limits as fundamental. The tension between these views enriched physics and deepened humanity's understanding of the universe. Through his engagement with Einstein, Niels Bohr demonstrated that scientific progress depends not only on discovery, but on dialogue, disagreement, and philosophical reflection. Their debates transformed quantum mechanics from a technical framework into a profound statement about the nature of reality itself. Niels Bohr's influence on physics did not end with equations, models, or philosophical arguments about reality. Perhaps his most enduring contribution was the creation of an intellectual environment that shaped generations of scientists and defined how modern physics would be practiced. Bohr was not only a revolutionary thinker, he was a builder of institutions, a mentor of minds, and a quiet architect of the scientific culture of the 20th century. His vision extended beyond discovering how atoms behave to cultivating a global community capable of asking deeper questions about nature itself. At the center of this legacy stood the Institute for Theoretical Physics in Copenhagen, later renamed the Niels Bohr Institute. Founded in 1921, the institute quickly became the world's most important hub for quantum research. Scientists from across Europe and beyond traveled to Copenhagen not merely to learn technical skills, but to participate in an open-ended conversation about the meaning of quantum theory. Bohr deliberately designed the institute as a place of discussion rather than hierarchy. Doors were open, debates were encouraged, and even the youngest researchers were invited to challenge senior figures. This atmosphere was radically different from the rigid academic traditions of the time. Bohr believed that physics advanced not through isolated genius alone, but through sustained dialogue. He often spent hours walking with colleagues, circling the same ideas repeatedly, refining language, questioning assumptions, and probing conceptual weaknesses. Many visitors initially found his style frustrating. Bohr spoke slowly, hesitantly, often revising his sentences mid-thought. But over time they realized that this process mirrored his philosophy. Understanding, for Bohr, was not instantaneous clarity, but something earned through patience and collective effort. The Copenhagen Institute became a magnet for the brightest minds of the era. Werner Heisenberg developed matrix mechanics there. Wolfgang Pauli refined the exclusion principle through intense correspondence with Bohr. Paul Dirac, Pascual Jordan, and many others passed through its halls. Even Albert Einstein, despite his disagreements with Bohr, engaged deeply with the Copenhagen Circle. In this way, Bohr shaped quantum theory not just through his own ideas, but by creating the conditions in which others could flourish. Mentorship was central to Bohr's identity. He treated students and collaborators not as subordinates, but as intellectual partners. When younger physicists struggled, Bohr rarely provided direct answers. Instead, he asked questions, often deceptively simple ones, that forced them to confront their own assumptions. This method cultivated independent thinking and intellectual courage. Many of Bohr's students later became leaders of physics in their own right, carrying his influence into universities and laboratories around the world. Bohr's impact also extended into the ethical and social dimensions of science. Having lived through 2 world wars and witnessed the rise of nuclear weapons, he became deeply concerned about the responsibility that accompanied scientific power. During World War II, Bohr escaped Nazi-occupied Denmark and worked briefly on the Manhattan Project. Yet even as he contributed to the development of nuclear technology, he remained troubled by its implications. After the war, Bohr emerged as a leading advocate for international cooperation and openness in science. He argued that secrecy in nuclear research would lead to mistrust and conflict, and that only transparent collaboration could prevent catastrophe. Bohr's famous open world philosophy called for shared knowledge as a foundation for peace. Though his proposals were politically unrealistic at the time, they anticipated later efforts toward arms control and scientific diplomacy. Bohr's moral authority stemmed not from political power, but from intellectual integrity. He understood that science could no longer exist in isolation from society. The same quantum discoveries that revealed the structure of matter had also unlocked unprecedented destructive potential. Bohr believed scientists had a duty to engage with these consequences honestly, even when doing so was uncomfortable or unpopular. Recognition of Bohr's contributions came in many forms. He received the Nobel Prize in Physics in 1922 for his investigations of atomic structure and radiation. Yet he regarded awards as secondary to the ongoing pursuit of understanding. His true pride lay in seeing ideas evolve, mature, and sometimes even outgrow his original formulations. Unlike many pioneers, Bohr did not cling rigidly to his early work. He welcomed revision and reinterpretation as signs of progress. Even after his death in 1962, Bohr's influence remained deeply embedded in physics. The Copenhagen interpretation continued to dominate discussions of quantum mechanics, whether embraced or contested. Later developments, quantum information theory, decoherence, and experimental tests of foundational questions, still grappled with concepts Bohr had introduced decades earlier. His insistence on clarity of language and careful distinction between what can be said and what can be known remains relevant in modern debates about reality, consciousness, and measurement. Perhaps most remarkable is how Bohr reshaped the identity of the physicist. Before quantum theory, physics aimed to describe an objective world independent of observation. Bohr helped transform this goal into something more subtle, an account of how nature reveals itself through interaction, experiment, and description. This shift required humility as much as brilliance. It demanded acceptance that human knowledge has limits, and that those limits are not failures but fundamental features of the universe. In this sense, Bohr's legacy is not confined to quantum mechanics alone. It represents a broader philosophical transformation in how science understands truth, certainty, and explanation. He taught that progress sometimes means abandoning the comfort of familiar concepts and learning to think in new, even paradoxical ways. He showed that disagreement can be productive, that uncertainty can be illuminating, and that collaboration can be as powerful as individual insight. Niels Bohr was not merely the father of quantum theory in a technical sense. He was its guardian, its interpreter, and its moral conscience. Through his ideas, institutions, and mentorship, he shaped the trajectory of modern physics more profoundly than almost any other scientist of his time. His legacy lies not just in textbooks and equations, but in the very way scientists think, argue, and seek understanding in a world that refuses to be simple. The significance of Niels Bohr's work extends far beyond the models, equations, and debates that defined his lifetime. His contributions transformed not only the way physicists understand the atom, but also the intellectual culture of science itself. Bohr's ideas laid the foundation for the entire field of quantum mechanics, establishing principles that continue to guide both theoretical investigation and experimental practice. While subsequent generations of scientists built upon and refined his models, the core insights Bohr introduced remain central to modern physics, illustrating the depth and enduring power of his vision. One of Bohr's most important legacies is the conceptual framework he provided for interpreting quantum phenomena. The Copenhagen interpretation, which he helped articulate, remains one of the primary ways physicists understand the strange and counterintuitive behavior of particles and waves at microscopic scales. By emphasizing the role of observation, measurement, and the contextual nature of physical properties, Bohr established a way to reason about quantum systems that reconciles formal mathematical predictions with experimental reality. This framework has guided countless experiments and continues to shape debates about the interpretation of quantum mechanics, including discussions of entanglement, decoherence, and quantum information. Bohr's insistence on the fundamental limits of knowledge also has profound implications. He showed that certain questions about quantum systems cannot be answered in absolute terms. The properties of particles are defined only in relation to the experimental arrangements used to measure them. This realization forced a shift in scientific thinking, from seeking ultimate deterministic explanations to developing probabilistic and operational frameworks capable of accurately predicting outcomes. Modern quantum theory, including applications in atomic physics, condensed matter, and particle physics, relies on this understanding of probability as an essential feature of the microscopic world. Equally significant is Bohr's influence on the scientific community through mentorship and collaboration. The environment he cultivated at the Institute for Theoretical Physics in Copenhagen fostered the growth of some of the 20th century's most brilliant physicists. Figures such as Werner Heisenberg, Wolfgang Pauli, and George de Hevesy were not only shaped by Bohr's ideas, but also by his approach to scientific inquiry, careful, methodical, and open to questioning. By encouraging rigorous debate and emphasizing conceptual clarity, Bohr ensured that the next generation of physicists was equipped to extend quantum theory beyond the hydrogen atom and to develop new techniques for exploring the subatomic world. Bohr's influence is evident in the technological revolutions that emerged from quantum mechanics. His pioneering work on atomic structure and quantization underpins modern electronics, lasers, semiconductors, and nuclear energy, the very devices that form the backbone of contemporary society. From computers to medical imaging, equipment rely on principles he helped establish. In this sense, Bohr's legacy is not merely theoretical. It has profoundly shaped the material world and the daily lives of billions of people. Beyond practical applications, Bohr also reshaped the philosophical approach to physics. By emphasizing complementarity, the contextual nature of measurement, and the limits imposed by quantum behavior, he encouraged scientists to confront the boundaries of classical intuition. Bohr's perspective suggested that understanding the universe may require embracing apparent paradoxes and contradictions, recognizing that multiple descriptions may be necessary to capture the full complexity of reality. This attitude continues to influence contemporary physics, from quantum field theory to studies of the fundamental nature of space and time. Bohr's engagement with ethical and societal concerns further solidifies his lasting impact. His reflections on the consequences of nuclear research and his advocacy for openness and international collaboration exemplify the responsibilities of scientists in a world shaped by their discoveries. Bohr's efforts to promote dialogue about nuclear weapons and global security demonstrated that scientific insight carries with it moral obligations. Today, the discourse on science and ethics, particularly in areas such as artificial intelligence, biotechnology, and nuclear technology, echoes the concerns Bohr raised decades earlier. The debates Bohr engaged in with Albert Einstein also continue to resonate. Their intellectual confrontations clarified fundamental questions about determinism, reality, and the role of observation in physics. These discussions laid the groundwork for later experiments, such as those testing quantum entanglement and Bell's inequalities, which have deepened our understanding of non-locality, information, and the foundations of quantum mechanics. Bohr's insistence on careful reasoning and conceptual precision in these debates set a standard for rigorous scientific discourse that remains relevant today. Bohr's enduring influence is also evident in the culture of physics itself. He demonstrated that progress often comes not from simply collecting more data, but from rethinking assumptions, questioning long-held beliefs, and developing new conceptual frameworks. His approach emphasized clarity of thought, intellectual humility, and openness to critique, qualities that continue to define the scientific method in the modern era. Bohr's combination of rigorous analysis with philosophical reflection offers a model for approaching problems that are both complex and foundational. In education, Bohr's work continues to inspire generations of students. His atomic model, the concept of energy quantization, and his ideas about complementarity remain central elements of physics curricula around the world. By demonstrating the necessity of reconciling abstract theory with experimental evidence, Bohr provided a paradigm for learning and discovery that emphasizes both imagination and precision. For aspiring scientists, his life and work exemplify the interplay between creativity, rigor, and mentorship that drives scientific advancement. Ultimately, Bohr's legacy is multifaceted. He transformed our understanding of the microscopic world, established principles that guide modern quantum theory, mentored the leaders of the next generation, influenced technology and society, and reshaped the philosophy of science. His insights into the limits and possibilities of knowledge, the role of measurement, and the necessity of conceptual innovation continue to shape physics in ways that extend far beyond his own era. Niels Bohr did more than describe the atom. He transformed the very way humanity thinks about nature, knowledge, and the pursuit of understanding. Through his life, work, and ideas, Bohr left an enduring imprint on both science and culture. His intellectual courage, philosophical insight, and dedication to mentorship created a framework that allowed the quantum revolution to flourish. Even decades after his passing, Bohr's vision continues to guide researchers, challenge assumptions, and inspire the exploration of the fundamental questions that define our understanding of the universe. In every sense, the influence of Niels Bohr remains alive in the questions we ask, the experiments we design, and the ways we seek to comprehend the natural world.